So now we need to calculate the sum of the present value of these cash flows. I'm going to split the dividend stream into two parts. The first part dealing with growth for the first 10 years, and the second part will deal with the dividends after those 10 years. Breaking the solution up into these components just makes it easier by reducing the mental overload. Once we've written down the sum of the present values, we need an easy method to calculate that sum. One of the methods you can use is to use compound increasing annuity theory, and this is the method that I'll be following for this particular problem. So let's write out the present value of the first cash flow stream, and I'll denote this by the symbol P1. Remember that we are working with a rate of return of 7% per year. So this means the cash flows need to be discounted using an interest rate of 7%. Applying this information, we discount the first cash flow for 2 years from time 2 to time 0, and we indicate that with v squared. Now, for reasons that will become clear later on, I'm going to indicate the percentage applicable for this discount factor. In this case, we are just discounting by the 7% return that the investor would like to earn on the share. So we'll deal with the second term, and we'll say the present value of this term is d multiplied by 1.06 times v to the power 3, because we are discounting from time 3 to time 0. Now, because we chose to split the dividend payment stream into two components, the final term that we'll include in this summation is the dividend payment before the growth rate changes from 6% to 3%. So this will be the value at year 12. This value is just d times 1.06 with 10 years worth of growth multiplied by v to the power 12. To use compound annuity theory, the exponent for the discount factor needs to be the same as the exponent for your growth factor. So in this case, n and m needs to be equal. So if you look at our first term, it doesn't have a 1.06, but we can add one, right? So we know from the laws of exponents that any number to the power 0 is just equal to 1. So we can rework the first term, which is d times v to the power 2, as d times 1.06 to the power 0, because we're not changing the value, we are simply multiplying by 1 times v squared at 7%. I'm going to go ahead and substitute that value for the first term. Now remember that for a compound increasing annuity, we want the powers of the discount factor as well as the power of the growth factor to be the same. That's a crucial requirement to work with compound increasing annuities. Now in our example, we have different exponents. So if we look at the first term, we'll see that that is equal to d multiplied by 1.06 to the power 0 times v squared. So the exponent for the growth rate is 0, while the exponent for the discount factor is 2. So there's a difference of 2 between these two values, and therefore it does not meet the requirement to use compound annuity theory. We can look at term 2 and we'll see that the same applies. This is d multiplied by 1.06 times v to the power 3. So in this case, the growth factor has an exponent of 1, the discount factor has an exponent of 3. So again, the difference between these two is equal to 2 units. There are a few ways you can tackle this problem, but in my experience, the easiest is to take out a common factor to get these exponents to be the same. So let's consider term 1. So we are taking out a common factor of v squared, and then the exponent of the growth rate will be 0. The exponent of the discount factor will also be 0 or 1. Remember, v to the power 0 is just equal to 1. And now we have equal exponents. The same holds true for term 2. If we take out v squared as a common factor, what remains is the growth factor, which is 1.06 to the power 1 times v to the power 1. So now these terms have the same exponent. So now we know that if we take out v squared as a common factor, we should have a situation where the two exponents are the same. So here we have d to the power 1.06 to the power 0, and I'm just writing this for your benefit so you can see that the exponents are indeed the same. V to the power 0, which means that if you multiply v squared by v to the power 0, yes, you get back v squared. So we've correctly adjusted this term. The second term, which is this one, I've already shown you that when you take out v squared, you are simply left with 1.06 multiplied by v at 7%. So now again, the exponents for the growth factor and the discount factor are both equal to 1. You'll see that this pattern continues. So for the third term, we have d times 1.06 to the power 2. We haven't touched the growth rate, but we have to lower the power for the discount factor by 2. And then we have the situation that we're looking for. Plus dot dot dot, and of course we have to deal with the final term, which is just d times 1.06 to the power 10, and we are left with a discount factor to the power 10. So the first term is really just d multiplied by 1. From the theory of compound annuities, we will replace 1.06 multiplied by v with a new discount factor that we will just call w. This new discount factor has a new interest rate that we need to calculate. In the same way, we are going to replace 1.06 squared times v squared with wj squared. We'll continue along this fashion, and the last term will become w to the power 10 at interest rate j. If we take out d as a common factor from all of these terms, we end up with a new equation, d times v squared at 7%, and then the first term we are just left with a 1. In the second term, we are left with w at interest rate j. The next term is w to the power 2 plus up until the final term for the first part of the dividend stream, which is just w to the power 10 at some interest rate j. Now this pattern should be familiar if you know your annuity theory. This is an annuity due for some duration n. Importantly, since the first term is 1, it means that our first payment occurs at the beginning of the first year. So this is not an annuity in arrears. Now the second trick that I often see students stumbling is the calculation of n, which is defined as the number of payments under an annuity due. It's tempting to look at the highest exponent in this equation and to say that this is an annuity due over 10 years, but this would be incorrect. I'll do a quick reminder on the cash flow pattern for an annuity due, just because this is such a common mistake made by students. So we know that for an annuity due, all the payments are equal to $1. And we also know that those payments are made at the start of each year, which means that the first payment is made at time 0, the second payment is made at time 1, a third is made at time 2, and so on. And the final payment is made at the start of year n, which is at time n minus 1. So if we write down the equation for the present value, this is 1 plus v to the power 2 plus intermediate terms, and your final payment has an exponent of n minus 1. So what's important to see here is that the highest exponent in the formula for the annuity due is 1 less than the term. So term minus 1 is equal to the max exponent. That means if you have the max exponent, it's very easy to work out the term. You just add 1 to the max exponent. In our example, the maximum exponent is 10, so n will be equal to 10 plus 1, which is 11, and not 10. So this formula reduces to an annuity due over 11 years at a new interest rate J that we'll get to in a second. So the hard part is done. All that is left for us to do is to calculate the interest rate J that applies to this annuity due. To do this, we go back to the definition of W. So we know that W at J is just equal to 1.06 multiplied by V at 7%. Now the discount factor we can just write as 1 plus the interest rate to the power negative 1. On the right hand side we have 1.06, and we know what the interest rate is. It is the 7% that we have been given by the problem. So we simply rearrange this, and we end up with J is equal to 1.07 divided by 1.06 minus 1. If you work this out in your calculator, this is 0.00094333962 on my calculator. Now what is important is you need to remember that your calculator displays a fixed number of digits depending on what will fit into the screen. And this may be different depending on the model that you are using. But importantly, in the background, the calculator will work with more decimal values to ensure that your final answers are accurate. So what's really important is to store this value in the calculator's memory and to recall that value when you need it instead of typing it out. If you don't know how to use the memory for your specific model, there are many good tutorials for all the different calculator models out there. So finally, if we want to calculate an annuity due over 11 years using the interest rate J, and we now know what the value of J is, we need to remember the formula, and that is 1 minus V to the power N, which is just 11 in this case, divided by D, and again, D is based on the interest rate J. So now all that remains is to calculate this formula. Fairly straightforward, and I'm not going to spend a lot of time on this. This will be 1 plus j to the power minus 11. And the definition of d based on an interest rate j means that we need to substitute the bottom for j divided by 1 plus j. My calculator shows that this value is 10.50013. So now we can work out the value for P1. We substitute D for 20 US cents. This is the value of the first dividend payment that was provided by the word problem. We multiply that by V squared at 7%. That is 1.07 to the power minus 2. And finally, we have the value for an annuity due over 11 years at this new interest rate, which is just 10.50013. It is important to note that the discount factor we have to the left of the annuity uses the original interest rate or the rate of return of 7%. It does not rely on the interest rate J. This is quite a common mistake made by students. When I multiply all of these digits, and of course I have stored this value in my calculator's memory, I obtain 1.834244. Phew, that was hard work. I promise you that we are almost ready to approach for landing. Well done if you managed to understand and follow the work that I've done. If you struggled, I would really recommend you revisit the theory on compound increasing annuities, as that is really the core to solving this particular problem. Please remember that this exam cannot be beat by observing others. You have to try these problems for yourself. So I would strongly recommend that before you watch the next installment, that you try for yourself to value the remaining cash flows, and then we compare notes. As always, any comments or suggestions are very welcome, and thank you for watching.